How's it going, everybody? In this video, we're going to talk about using inverse trig functions because I noticed that a lot of people are struggling and they're using up a lot of time on tests and even when they're just trying to solve basic problems in using inverse trig. So here's a little bit of explanation of what's going on here. Trig inverse functions, I underlined and emphasized functions because they have to be functions, which means they have to sort of pass the vertical line test. Well, what does that mean? If we're not talking visually, it means that we can't have two different y values for a single x value. And so we have to make sure that our inverses are functions. A lot of times when we get a function and we try to find its inverse, we might not know right away if its inverse is an entire function. So here's what we take a look at. We're looking at trig functions, sine of theta. Sine of theta has these y values, right? They fluctuate, starting at 0, going upwards, coming back down to 0, going through the negative, and then at the end of the period reaching 0 again. Well, we can't just flip the x and y's for this and call it sine inverse. We would like to, but we cannot just do that of flipping the x and y's and calling it sine inverse, because if we do that, we're going to have several different locations with the same exact input, but they have different outputs. And so what we want to do is we want to take a strip of sine, not the whole thing. We just want to take a strip of it where it covers its entire range. So let's talk about the range of sine of theta, which is from -1 to 1. We just want one strip of this function. And when I say strip, I just mean like a little piece, right? Like maybe we can take this piece, or maybe we can take this piece. We just want a specific piece that is going to satisfy all of the y values with that piece. So if we start from the bottom here at -1, that's its lowest y value, and we take this strip that goes all the way up to the top at +1, that's going to be enough of a strip for us to turn that into sine inverse, because it's going to cover every y value that sine has. So that's enough x value on our sine inverse. And where are these located? This is pi/2, and this is -pi/2. Okay, so just keep in mind that our domain, or our x values on sine of theta, is going to correspond to our y values on sine of theta. So that means that the range of sine of inverse of theta, our range of sine inverse is going to go from -pi/2 to pi/2, because that covers all of the possible values for sine. Let's take a look at cosine now, and let's keep that range in mind. We'll take a look at this again on the unit circle. Let's look at cosine of theta. Cosine of theta begins up at max amplitude or max distance away from the midline. And so we notice that if we want to take a strip of cosine to cover its whole value, even though it extends to the left, I'm not going to look at that portion. It starts here at the top, so I might as well start here at theta equals 0 and follow this curve all the way down to the bottom. Kind of didn't follow it very well. That's a little bit better. And how far does this go? Well, this goes from 0, of course, all the way to pi, and that's going to cover the entire range of cosine. So hopefully you understand what we're doing here. We're trying to cover the entire range of cosine or sine, but only once. We don't want to repeat y values. We just want to cover the range once. So since the range goes from -1 to 1, but it achieves that on the domain from 0 to pi, then when we turn it into an inverse, we're going to switch the x's and the y's. We're going to switch the input and the output, or you can think of it as we're going to switch the domain and the range. And so now the range, or the output of cosine inverse, is just going to give you from 0 to pi. And now this is very important to consider if you're using cosine inverse, for example, when you're plugging this into a calculator. You're only going to get angles between 0 and pi. You're not going to get anything greater than pi. You're not going to get 3 pi/2. 5 pi over 4, 7 pi over 6. You're not going to get those values from doing the cosine inverse function, because those values are further down the line on the cosine graph where the y values have already been repeated. And so I don't need to represent those values. The calculator will not tell you about those values. The calculator will only tell you about values from 0 to pi. And so we should also only give out values from 0 to pi when we're doing the cosine inverse. Okay, lastly, let's look at tangent so that we can get an idea of the range of tangent. Tangent, you can see, goes all the way from negative infinity to positive infinity. Oops, no brackets on infinity ever. So the range of this goes from negative infinity to positive infinity. But where does that happen in between on the domain? That happens similar to the domain for sine. It goes from negative pi over 2 to pi over 2. You might remember that that's where these asymptotes are located. This is, I guess I won't say x, I'll say theta equals negative pi over 2. And this is theta equals positive pi over 2. So that means the range of our tan inverse, similar to the sine inverse range, the range on tan inverse is just going to be from negative pi over 2 to pi over 2. All right, now let's look at those ranges of the inverse functions. Let's look at those on a unit circle diagram. Here it is. So if we're looking at this as a unit circle, this angle represents negative pi over 2, and this angle represents pi over 2. It's the same location as 3 pi over 2, but 3 pi over 2 is what you get when you see a whole arc going all the way around like that. We're actually going backwards, and so that's a negative pi over 2. Here's the angle from 0 to pi, or if you're in degrees, 0 to 180 degrees, and also for tan inverse from negative pi over 2 to pi over 2. So what does this mean for you? What does this mean for solving problems? This means that whenever we have to draw a triangle according to an inverse of a ratio that is given, we'll see plenty of examples, we're only going to consider drawing them in these locations. And you'll notice that each of these quadrants, there are 2 quadrants for each of the inverse ranges. Each of these quadrants represent a positive and negative for the sine function, for example. Positive would be up here, negative would be down here. For the cosine, positive is in the first quadrant, negative is in the second, and for tangent as well, as the sine inverse, positive is in the first quadrant, negative is in the fourth quadrant. So like I said, this is what it means for you. So this is really the most of what you should absorb, is that you're going to be drawing triangles in these quadrants whenever we're doing inverse trig. That doesn't mean you're only ever going to draw triangles in these quadrants. If it's a different type of problem, which I might make a video on, who knows, a different type of problem that gives you the values of sine or values of cosine and tells you this is positive, this is negative, and you have to find where on the unit circle that's located, that's a different type of problem. But if we're using inverses, and I'll show you exactly what those look like, we're only going to be using these quadrants to draw our triangles. Okay, so let's look at some problems, some quick ones here. Now these come from the unit circle, so you should know them kind of quickly, but I also just want you to be able to imagine visually where this is located. Sine inverse equals 1/2, or rather sine inverse of 1/2. Since that's positive, all I want you to think about for right now is that it's associated with a triangle that looks like this, with an opposite side of 1 and a hypotenuse side of 2. I don't even need you to find the other third side. Feel free to find the other third side if you'd like to, but I really just want to make sure that you know where that's located at. That way we can predict the angle. So of course this is going to be pi over 6 or 30 degrees. Now it is true that there is another angle which has a sine value of 1/2, but it's not in the range of the function. So even though the angle that's out here with the opposite of 1 and a hypotenuse of 2, that would be 5 pi over 6. Even though 5 pi over 6 does have a sine value of 1/2, when we're doing the inverse, we're only considering angles that are along this Oh, wow, that was pretty bad. We're only considering angles that are along these two quadrants. And that's what your calculator will tell you as well. So that's the point I'm trying to make, is that you should expect your calculator to give you this value. It won't give you that other value. Let's look at the cosine of 1/2. Adjacent over hypotenuse is 1/2. We could only consider these first two quadrants, and since it's positive, it's again going to be in the first quadrant. It's technically going to look a little bit different because the adjacent now needs to be 1, but we're not worried about drawing everything to scale. You don't have to worry about drawing everything to scale. Okay, and what angle would that be? This is great practice for you to look at. You could plug it into a calculator, but you should know this from the unit circle. If you don't know these right off the bat, then you need to study the unit circle more. And then we have tan inverse of positive rad 3/3. So of course it's going to be in the first quadrant. Tangent is opposite over adjacent, so this is rad 3, and this is 3. Okay. Pretty good so far. Pretty good. And this, I believe, is like 2 rad 3, I think, but it's not really important. I just want you to know where these angles are going to be drawn, where the triangles are going to be drawn. So arc is the same thing as inverse, just to let you know. So arctan is tan inverse, arcsine is sine inverse, arccos is cos inverse. Let's take a look at this. Arcsine of negative 1/2. So now we're not going to draw it in this positive quadrant. Now for arcsine, which is kind of weird. They put arcsine inverse. That's bad notation. That was a mistake, whoever did that. It should either say sine inverse or it should say arc. So maybe they had sine inverse first and then they just wrote arc in front by accident. Where's this going to be located? It can only be located somewhere in the first and the fourth quadrant. So of course this is going to be in the fourth quadrant. So we have -1 and 2. So that's going to be negative pi over 6. That's another reason why I'm showing you guys this, because this angle is going to be written as negative pi over 6, not 11 pi over 6. Your calculator is not going to tell you that it's 11 pi over 6. It's going to say negative pi over 6. Or if you're in degrees mode, it's going to tell you negative 30 degrees. Okay, you guys get the vibe here? So let's take a look at this one. Our cosine of negative 1/2, it can only exist in the first two quadrants. And if you don't remember why it can only exist in the first two quadrants, go back to the beginning of the video and make sure you're looking at how I break down a piece of the cosine function, and then it'll help you understand. Negative 1/2 is going to look somewhere around here with the adjacent of -1 and the hypotenuse of 2. If you plug this into a calculator, it's going to give you an angle between 0 and pi, or 0 degrees and 180 degrees. It's going to give you 2 pi on 3. Depending on your calculator setting or how it's programmed to give you the output, it might not give you the rational expression with pi. It might give you a decimal, so be careful of that. Like they might actually calculate 2 times pi, which is about 3.14 over 3. So it'll be like about 2, a little over 2. So if you see something like 2.03 or something, I don't know what it is, but it's 2.0 something. If you see that on your calculator, don't be scared and think like, oh, I did something wrong. It's just that your calculator didn't bother to use the term pi. It actually multiplied it because it's a calculator and it can do that. Okay, so arctan of negative rad 3/3. Again, we look at the quadrants where this could exist. It's kind of weird. It wasn't very round. It's a little more round. And it's in the negative side, so it's going to go over here with an opposite of negative rad 3 and an adjacent of positive rad 3. Notice that because the fraction's negative, only one of them has to be negative. Which one has to be negative? We'll just think about it logically, right? If it goes down, then this component is going to be a negative. And we're not saying that the length is negative. That's not really accurate. But what we're doing instead is we're putting a point on the circle which has these coordinates, and so that's why it's allowed to be negative. Okay. Oh, and also let's talk about what angle that is. That is negative pi over 6. I don't know if we looked at that for the other one. Yeah, I forgot to say this is angle pi over 6. Okay, so let's take a look at some more of these. Yes. These are some special cases where we're on the quadrantal angles, which means we're on like a 90 degree or 180 degree or negative 90 degree spot. Okay, so arc sine of 1, it's sort of hard to draw this, so we're not going to be able to draw it, but we need to ask ourselves, sine of what equals to 1? And since it's positive, it has to be up at the top. It literally has to be this spot up here that's positive, and the furthest that it can go is 1. So that confirms that theta is pi over 2. Our cosine of 1, it's negative on the second quadrant, positive on the first quadrant, so that's going to be right here at 0. Tan inverse of 0, well, on the top it's positive, on the bottom it's negative, and smack dab in the middle, it's 0. So that's also going to be 0. 0 degrees or 0 radians, they're the same. Okay, you get the idea. You can try a couple of these other ones if you'd like to. Plenty on here. There's 3 more here if you'd like to try those. But now what we're going to do is we're going to talk about doing the trig of an inverse trig. So now we have to be very particularly careful. And this is especially why I'm showing you the first step of doing the inverse correctly, because you need to know which angle we are talking about. So in this case of number 1, there are 2 angles which satisfy the equation sine of theta equals 1/2. Well, actually, there are infinite number of angles that do that. But on the interval from 0 to 2 pi, there are only 2 angles which satisfy that, pi over 6 and 5 pi over 6. However, when we're doing more stuff with it, it's especially important that we use the proper sine inverse value, because we're going to take a cosine of that sine inverse value. So first we would draw a little triangle. Remember, inverse, trig, these all represent angles. So that's why we draw triangles, because the triangle has a specific angle with a ratio that's given to us. So these are angles, but we need to find out what angle it is. So cosine of sine inverse of 1/2, that's going to be with a 1, that's going to be with a 2, which means this is really just cosine of pi over 6. Now the advantage of drawing a triangle is that you could just read this from the triangle. We're working with some trig expressions that are nicely on the unit circle, but even if this was not on the unit circle, I would still know how to draw it in the correct quadrant. If it's positive, it's going to go in the top quadrant. Let's see if we have any other ones that are like that. And this will be rad 3 over 2. If we were to solve this with the Pythagorean Theorem, or just kind of remember our special 30, 60, 90 triangles, that's rad 3. So the cosine is adjacent over hypotenuse. That's rad 3 over 2. Okay, let's look at something like this. Sine inverse of cosine pi over 3. Now this is giving us a specific value, and then we have to do the inverse afterwards. So cosine of pi over 3, what is that? That's just going to be 1/2. And there's only one possible value for that. So sine inverse of 1/2, looks like we keep seeing this quite a lot, sine inverse of 1/2. So by the end of this video, you should have that perfectly mastered, the sine inverse of 1/2. Okay, let's look at something a little bit different now. This is most interesting because number 25 says sine inverse of sine. You would think that the inverse of something just cancels it out perfectly. And it kind of does, but we have to be careful, because we can't just cancel these things out. Why not? That would give us 7 pi over 4. Well, why is 7 pi over 4 wrong? 7 pi over 4 is not in range. It's not in the range of sine inverse. Sine inverse only goes from negative pi over 2 to positive pi over 2. So this can't possibly give you 7 pi over 4. When I do sine inverse of something, I can't possibly get 7 pi over 4. This is why I need to be a little more careful. We first want to calculate sine of 7 pi over 4. And I understand that the angle 7 pi over 4, here's where some of the confusion is. Someone might say, well, 7 pi over 4 is right there. That's totally in the range, right? Isn't that where you drew it? It's in the 4th quadrant. That's where you drew it. See? 4th quadrant. That's where 7 pi over 4 is. Oh, except it's not being called 7 pi over 4 anymore. It's being called something between negative pi over 2 and pi over 2. So that's where a lot of the confusion comes from. it's not that you don't understand where the angle is at. You do understand where the angle is at, but in this case, if you're getting this wrong and just canceling the sine inverse, it's because you don't understand that sine inverse has a range from negative pi over 2 to pi over 2. So what's the solution here? Just take that angle, and instead of calling it 7 pi over 4, instead of insisting to call it 7 pi over 4, we have to call it negative pi over 4. And I'll break that down step by step. Because sine of 7 pi over 4 is negative rad 2 over 2. And so now when I draw that triangle, it's going to go in the negative space for sine. And I'm going to have negative square root 2, and that's a 2. And the sine inverse of that is a negative pi over 4. Okay, so don't let the sine inverse, the inverse idea, deceive you, because it does sort of mean that we're canceling this out, kind of, but you have to be careful to make sure that this value is in the range of your function, because if it's not, then we can't possibly have that be the value. Okay, let's look at another example that's kind of tricky like that. Actually, I don't think I have another one right here, do I? Let's see, is this a good one? This is a good one, I guess. Arc cosine of sine pi over 3. Sine of pi over 3, you should know this off the top of your head very quickly. Square root of 3 over 2. So we want to do arc cos of square root of 3 over 2, which means positive cosine. And that means I'm going to draw this there. And that means this is going to be my square root of 3. This is going to be my 2. So what angle is that? That's going to be, of course, pi on 6. This is a 30-degree angle here. Okay, and let's see. Last one here that we'll do, tan inverse cosine of pi. So cosine of pi, again, you should know this mentally. If it takes a second, that's fine. Negative 1. So we want the tan inverse of negative 1. Tangent can only exist, well, I should say tan inverse can only exist in the first and fourth quadrant. But the better way to say that is from negative pi over 2 to pi over 2. Because if I say first and fourth quadrant, you might think that an angle like 7 pi over 4 works. We're not allowed to call it 7 pi over 4. We're only allowed to call these angles something between negative pi over 2 and pi over 2. Negative 1 means that it goes in this corner. So that's a negative 1 on the opposite and the adjacent. So it's a negative 45 degrees, so to speak. So you can call this negative 45 degrees, or you can call it negative pi on 4. Excellent. Okay, and to finish up, we have some algebraic examples of how to represent this, which is a little trickier, but I think it's great. Once you've mastered the previous types of problems, you can start to use expressions like this. And these aren't even that complicated, but they're pretty nice because they require you to draw the triangle, and they also require you to finish the triangle, which I think is something that, again, students need to speed up a little bit. Let's go. We're starting with arc cosine of x over 3. If there's no negative indicated, we can assume that these are nicely in the first quadrant. So we'll draw something like that. Doesn't have to be drawn to scale, just make it arbitrary in the first quadrant. And the cosine is defined as the adjacent over the hypotenuse. So that means that this is the x side, this is the 3, and we're looking for the tangent of that. So we need the opposite and the adjacent. We do not have the opposite here, it is missing. So we're going to say that x squared plus, I don't know, let's call it b squared equals 3 squared. And I'm solving for b here. So we have that b squared equals 9 minus x squared. And so b equals the square root of 9 minus x squared. We would get plus or minus technically. Whenever we solve an equation with the square root, we have to consider the plus or minus case. But since this is in the first quadrant, we know that this is just going to take the positive. So we have square root of 9 minus x squared. And therefore, the tangent of the arc cos of x over 3 is simply square root of 9 minus x squared, that's the opposite, over the adjacent. So it got really algebraic very quickly. simply because one of the side lengths is a variable, and we have to just keep it as that variable. Okay, good. Let's take a look at the next. Sine of arc cos of x. Well, since there's no fraction here, you might struggle and say, well, what am I supposed to do with that? Well, if there's no fraction, you can just call it x over 1. You can make anything into a fraction. You can just divide it by 1. So that means the adjacent side is x, the hypotenuse is 1, and now again we have to do a little bit of a Pythagorean theorem and say that x squared plus b squared equals 1 squared, which is just 1. And by a similar argument as before, we're going to get that b is the square root of 1 minus x squared. But now we're looking for the sine. 1 minus x squared. Now we're looking for the sine. So the sine of this, I guess I can put that there. Kind of messy. I'll just put it straight down. Put that down here. Is the opposite side, the square root 1 minus x squared, over the hypotenuse, which is just 1. So actually that's also the sine value. Okay, looks good to go. And the last one here. Arctan of x over 2. We're going to draw a triangle that associates to that in the first quadrant because we have no reason to think that it's negative. If we have a reason to think it's negative, we can draw it in the negative region, but we have no reason to think that it's negative. Tangent is defined as opposite over adjacent, so we can label this x and 2, and we want the sine value, which means we need the opposite over the hypotenuse. So let's do some Pythag. Here we're missing the hypotenuse this time, so we're going to say that x squared plus 2 squared equals, I don't know, c squared. It makes people happy when we use c for the hypotenuse for some reason. So we're going to call this the square root of x squared plus 4. That is the hypotenuse. Okay, now let's find the sine because we need to do opposite over hypotenuse. And I suppose if your teacher wants you to rationalize this, you could rationalize it. You could go ahead and multiply root x squared plus 4 over root x squared plus 4. I don't really care about these such things, but if your teacher really does care about it, then we can appease them. Make sure you're getting full points. You don't want to miss points just because you have a picky teacher. And so those are equivalent, but I guess that's rationalized. And that's a good place for us to finish.